Hi everyone, I am coming to you from the lab. I came up here to the lab to do this demonstration, but guess what? You get to do it at home. I think it's something that you can do at home. We'll see. I have on my gloves that I got from the cafeteria just to try to be safe. I'm also making sure that I wipe stuff down with Clorox wipes, so when you get this stuff, hopefully it's all sanitized and no worries there. What you will be getting if you come to the pickup on Tuesday to pick up information, I will also have a baggie that looks like this. And so what I'm putting in these baggies is a 16-ounce styrofoam cup and it says an 8.5 ounce styrofoam cup. So a small styrofoam cup and a little styrofoam cup. You're gonna get, it'll be one of these cups. The little one is inside there, nested inside there. And then also you'll have a weight. I have weights that vary and it says it on here. So you probably cannot see this. Maybe you can't see this, but when you get it, you'll see it. This says 200 grams. I have weights from 10 grams all the way up to 200 grams. So you'll be getting something different. However, all of them are made of the same material. So that's in your baggie that you're gonna get. And I'm gonna explain to you right now, hopefully this is helpful, how to do this lab and how to put it together. All right, so what we're doing is calorimetry. Hopefully you have looked at my information about calorimetry and what it is, why we use it, how it's used to measure heat transfers. And so we're going to use the simple coffee cup calorimetry. It's a very basic setup. Your calorimeter is just a styrofoam cup. The reason why we're using a styrofoam cup is because we want to try to make it an isolated system. In an isolated system, there's no heat transfer into the cup or outside the cup. So basically what all the process, it's actually a physical process. You can do this with chemical reactions, but it's a physical process. It's all gonna happen inside the cup. So we don't have any like heat transferring that comes from our, our surroundings. So it's gonna be inside there. To try to make this a more insulated, oh, sorry, that noise. You're gonna use the smaller cup to be sort of the lid. So notice how that kind of fits as a lid. It's so super sophisticated, isn't it? Anyway, this is going to be our calorimeter. Now, there is an issue with the thermometers. You obviously has to have a thermometer to measure this heat, to measure the temperature change. And we're going to do it in Celsius. So I have found a few thermometers around the lab that I can give to you. Some of them will fit nicely in the bag because they're kind of small. And I'll put those in the baggie, so you might get one in the baggie, or you may have a larger one. Honestly, this is Friday when I'm filming this video. Between now and Tuesday, I might put some kind of a question for you to see if, hopefully I've been able to touch base with you about the thermometers to see who needs what. Either way, hopefully you'll use a thermometer. I have some suggestions on how to use that thermometer with our really great calorimetry setup here. If you happen to have a larger thermometer, I don't know what it is. So if you have a larger thermometer, what I've done with this particular setup is I just punched a hole at the top of this one. Makes a nice sound. Hold yours. So that now you have a thermometer at the top of this, and you can read the temperature as it's hopefully changing in your thermometer. I have some ideas about the smaller one, if you happen to get a smaller one, how you can still work this setup. I punched a hole on the side. You could stick the thermometer through that hole and still be able to read the temperature that's in the bigger cup. Alternatively, really, you could just stick the thermometer like that. Yes, we may be losing some heat if you do it that way, but however you want to get to where the thermometer is raised. The point of having the smaller cup is just to try to keep it insulated. If you happen to have any lids that fit on that, that would work great too. Just want to keep it insulated. And if you just had it out like this, then I'm afraid we might be losing some heat. So try to finagle the thermometer into this. Okay, so let's talk about that's the setup. Here's what you're going to do in the lab. The purpose of the lab is we are trying to find out what the specific heat of your metal weight is. And we're going to do that using calorimetry. So what you'll want to do is first you'll need to heat up your metal. So you're going to heat it up. I have right now a beaker on a hot plate with the metal inside, some water that's been heating for probably about 15 minutes or so, maybe more. This is not turned up really high. This is not something you have to have a beaker for. You can take just like your stovetop or even a microwave. I wouldn't put a metal in the microwave, but you can take your stovetop and boil some water, or get it just to the point of boiling. It doesn't necessarily have to be boiling. You put that, then put your metal in the hot water for a while. If you're doing it like I've done here, I put my metal in right when I first started this water. So it's been in the water, it's acclimated to the temperature of the water. If you're doing it in a microwave, like I said, don't put the metal in the microwave. If you're doing it in a microwave, then heat your water up first, then maybe cover it so that it doesn't lose too much heat. Put the metal in it, let the metal heat up from that water. The water that you put in this doesn't matter how much you put because you're not really using that. That's just to heat up the metal. So basically I'm heating this metal up for a while. I suppose it could also just heat the metal, but the reason why you want the water bath is because it's going to be easier to take the temperature. So let me grab whatever thermometer I'm using. Hopefully this follows along. And I'm going to take the temperature of this water bath. Okay, I'm not going to take too much time since this is just a demonstration, but it looks like it's about 60 degrees Celsius. If it was closer to boiling, you would think it would be more, maybe closer to 100. And as I'm talking, it's moving up. But this is where I would take the temperature of the metal, because the metal's in here. We'll say that the metal is 60 degrees. I also want to, so the metal is at whatever temperature that is. I'm going to fill up some water into my calorimeter. Because we can't, I'm assuming that you don't have balances, taking the mass is going to be tricky. So the metals that I'm giving you, as I mentioned before, have a mass on them. So you've got the mass of the metal. For the mass of the water, we're going to assume that the density of the water, if the density of pure water is 1 gram per milliliter. So let's say whatever water you're using is pure water. So if you want to use bottled water, I don't know if it's going to be that necessary to be precise, or accurate. You could use tap water. But I've measured out 250 milliliters. Notice I'm using a measuring cup that you probably have at your house. And I know I have one of these at my house. This one I found in the lab. But if you notice that there are milliliter markings on there, I've got that tilted now, but it's 250 milliliters. I don't know if you noticed when I put it closer, that's also about the same thing as a cup. A cup is 240 something milliliters, so we'll just say that it's 250. So if I'm putting 250 milliliters of water, the density of water being 1 gram per milliliter, then that means that that's 250 grams. Okay, so I've got the mass of my metal. I have the temperature of my metal, initially, the initial temperature. I have the mass of my water, which was 250 grams. I'm going to take the temperature of my water. I might as well go ahead and put this dilly whopper on. And this temperature, it's gone down from reading them there. It's about 20 degrees Celsius. So and my initial temperature of my water is 20 degrees Celsius. Okay, now we're going to do the calorimetry. That's the data that you need to put initially. You got initial temperature of your water. Initial temperature of your metal. Mass of your metal, mass of your water, initial temperature of your water. Now take your take your metal, and don't put your hand in boiling water or anything. Here's some safety issues. Get like some kitchen tongs or your brother or sister's hand. Just kidding, don't do that. I've got these tongs from the lab. You probably have something. You could just decant the water. That means you pour it out. Just be careful, don't burn yourself. And I practiced this so I wouldn't fumble too much. I didn't practice it well enough. Okay, so I've got my hot piece of metal and I'm going to put it in this water. Okay. Then after that, I will measure the temperature change. I would say wait a little bit. Make sure that it does, because let's talk about what's going on while I'm waiting right now. So what's happening here inside my calorimeter is that the metal has a certain amount of heat associated with it from just being in the hot water. It is going to, because of the second law of thermodynamics, the second law of thermodynamics is the one that says that basically temperature goes from, or heat will move from area of high temperature to area of low temperature. So just because of the second law of thermodynamics, that piece of metal is heating up the water. Notice that I'm kind of swirling it to stir it a little bit. You can probably also do that a little bit with your thermometer, depending on if you have the big or small thermometer. Because if you watch the video where the guy is showing the schematics of the bomb calorimeter, they actually have a stirrer in there too. So that's okay, because what we're trying to do is evenly distribute the heat among the water. All right, so I'm gonna measure the temperature of this water. And I get that the temperature has raised some. So I'd write down, then I'm going to write down what that is. I would, also want to say that you want your metal to be in the boiling, or you could do boiling, or just be in warm water for a while so that you can make sure that it heats up. And then you take the temperature, and that's your final temperature. So you get your final temperature, you get the mass of your water, you get the mass of your metal, you get the initial temperatures of your metal and your water, and then you can calculate the heat that is being transferred using that equation where Q is equal to the specific heat times the temperature change times the mass. And also we're going to use the first law of thermodynamics, saying that the temperature from the water is going to be, it's absorbed, so it's positive. The heat, I said the temperature of the water, the heat from the water is absorbed and it's positive. The heat, or the Q value for the metal, is given off, so it's negative, but it should be the same amount, the same value, just a different sign. There you go. That's the calorimetry lab. And if you have any questions, I think there may be an issue with the thermometers, but other than that, you should be able to get this and do it. Post your results. I'd kind of like to see pictures of you guys doing this. I think it would be interesting to put together some pictures of you all doing your lab at your house. I will also post something. I'd kind of like to see everyone's data. We'll do some sort of a share for the data. Let me know. I know getting it written in your lab notebook may be something that is a little difficult, but we'll work through it, and you'll get some credit for doing the lab, and hopefully it works out well for you. Bye.